All right, so I'm audible. Thank you so much. And so we can begin our live stream. Correct. Right, we are live. So I'll now start sharing and we can begin our.
Desktop 11 item selected. Your screen sharing is paused. Participants can now see your application. You have started screen share 100.
I'm going to talk about the culture media, the very, very basics of what we call as the kitchen of microbiology. And my guide was very fond of this statement when he used to tell me that it is the kitchen which determines how good a microbiology department is. Now, most of our laboratories have now shifted to a ready-made media, both whether it is for culture or for biochemicals. And for identification, many of us have also gone to um, what we call as the automated systems using Vitek or using Maldi. And so the technicalities of biochemical reactions and of culture media are not very clearly understood. But remember, all your examiners are old timers and they're very fond of asking about culture media, biochemicals, the quality control of culture media. So this session and the next session is going to talk about the culture media, biochemicals, and some amount of quality control as to how you check. That's also a very standard PG question where we ask how do you check the quality of the culture media. So what are the basic requirements? Now, we all understand that there are multiple basic requirements, and from our undergraduate knowledge, also, we know that any bacteria to grow, you require three or four things. One, it requires the nutrition in the form of proteins or peptides or amino acids. It also requires an energy source. Just like any other living organism, it requires an energy source in the form of, say, carbohydrate. The best form is glucose because it's a simple sugar. Then it also requires certain essential minerals and certain trace metals. Essential minerals like calcium, magnesium, iron, whereas trace elements like phosphate, sulfate, magnesium, and so on and so forth. Then there are certain buffering agents which may be needed because bacteria, as they multiply and they use glucose, they will generate acid, lactic acid. So that is going to bring down the pH. Sometimes we may require buffering agents so that our pH keeps coming up. To a certain extent, the buffering agent is able to maintain the pH. Then, for certain media and for certain biochemicals, we may require an indicator that we come to know what is the pH which has changed. And we also require certain selective agents. For example, if we want to grow certain organisms where there are a lot of commensals, we may require a selective agent like antimicrobials or heavy metals and things like that. Then we may also require certain gelling agents to make it solidify so that we can see the colonies properly. These may be agar, egg, serum, or gelatin. And of course, everything is 80% water, so we also require some water. So while culturing the bacteria, it's important that we provide all the environment and nutritional conditions which exist in their natural habitat. And some of these ingredients which we use are agar, peptone, casein, meat extract, yeast extract, and of course malt extract. So these are the organisms, these are the ingredients that are very much needed. So now, when you look at these constituents, what are the properties of each? First and foremost comes your water. Now, do I always require a double distilled water or a distilled water? If your potable or tap water has got a very high mineral content, then probably it's better to have a distilled water or a RO water which has low mineral content. But otherwise, it's not necessary that you require sterile water or double distilled water and you install big distillation plants in your departments. Primary sources of this is to liquefy everything, keep it content, provide hydration to the growing bacteria, and also act as a source of hydrogen and oxygen. Now, any water which is stored in copper vessels or has got through copper pipes can be detrimental. So, even small amounts can be very detrimental to bacteria. Any of the metals like copper, silver, so they should not be used. Then, sodium chloride and other electrolytes have to be proper. Now, coming on to peptone, we've heard this terminology such a number of times, but what exactly they are? They are partially digested proteins which either come from a lean meat or they come from a source of meat like the heart muscle or from casein or fibrin or soya. Nowadays protein is such a hyped compound. So whatever you are thinking in terms of eating a protein, the same can be used to source your peptone from there. Peptone powder that you get, which is ready made in the market, it's actually a hygroscopic substance. So remember that you have to close it, keep it in a closed container at a cool, dry place so that it doesn't become sticky when it is exposed to air. What does it contain? It contains proteoses, amino acids, it contains inorganic salts, and it also has certain accessory growth factors which may or may not be present naturally and may have been added from top. Then the peptone can vary in their quality. Primary function is that they provide support to moderately accepting bacteria. And there is no fermentable carbohydrate in this. So they should not contain any lactose or any glucose, which is a fermentable carbohydrate. That is why you see dairy is missing from here. We don't use dairy as a protein source because dairy protein contains lactose, and very often we may have organism utilizing lactose producing acid, and that may not work for that particular bacteria. Then there should not be any contaminating bacteria and it should not have any copper or any other detrimental effect which are there. Then what are the various types? There is a normal peptone which we use in all our laboratories in peptone broth or water, or there may be a special protein like a neopeptone which we used in a highly purified form, very little accessory growth factors and contaminating bacteria. And we also have a which is used for SDA, and we also have proteose peptone which we use for Bod and Genju medium. So similarly, we have peptones which are suited for different purposes. All right, now coming on to the most important part, which I am very fond of asking PG students, solidifying agents. So agar, we all know, is prepared from a seaweed. Now these seaweeds are plenty. They can be Gelidium, Eucadema, Pterocladia. All these seaweeds actually contain long chain polysaccharides of D-galactopyranose units and a very small amount of protein-like material, long chain fatty acids, and traces of inorganic salts like calcium and magnesium. Now, why do we prefer agar? You all know the story of, Frau Hesse, who was the cook for Robert Koch, where she realized that every time is gelatin is used, and just before visualizing the colonies, the gelatin plates have to be kept in the fridge so that it solidify. So that's why she used to use agar in her jellies, and that is what was used to cultivate bacteria. Its properties are that it is bacteriologically inert. It doesn't get damaged by autoclave. It doesn't break down by autoclave. And it does not alter the pH of medium because nothing is getting metabolized, so the pH doesn't alter. The best part is that it melts at 98 degrees and solidified at 42. So it's a different temperature. It's not like this. It's giving you a very broad range. And it is completely non-nutritive. So you know that what is the nutritional requirement of bacteria when you are checking for research or any other purposes. You know that agar is not adding any nutrition. The problem with gelatin is that it gets liquefied by a number of bacteria and it melts at 24 degrees and remains liquid at room temperature. So, as I said, it has to be refrigerated before you go ahead. Now, what are the dairies varieties across the world? First variety is New Zealand variety, which is more gellifying, and there is another one which is Japanese variety. In a solid preparation like a blood agar or nutrient agar, usually 2% is used. Another Viva question. For semi-solid, 0.5% is used. Solid agar, the more solid you make it, it is going to inhibit certain properties of bacteria. For example, if you reach up to 5 to 6%, it's going to inhibit swarming. It may reduce the size of colonies if your media is too solid. If your media contains less agar, while culturing, you might actually tear apart the medium and it may not work. Then what are the various, how do you prepare it? The appropriate amount of agar powder as per the recipe is added to water and the mixture is dissolved and sterilized by heating it in a steamer. So what you do is that initially also to dissolve it, you will need some warm water or hot water. It's not a boiling water, but you have to keep it in a steamer at 100 degrees and you add agar. Agar doesn't dissolve in cold water, especially so when you are in having ACs are running or winter is there. So when this molten agar comes to 45 degree, that is when you pour it in the petri dish and allow it to set for 20 minutes. How much amount you require per petri dish, which is 90 mm? Somebody please put it in the chat box. For a 90 mm plate, how much agar media do you require to produce a media which is 4 to 5 millimeters thick? Now, another constituent is casein hydrolysate. Now, casein is a milk protein. As I said, we don't use milk or dairy product in to generate protein. So where do we use it? We use it in here to generate what is known as the casein hydrolysate. Casein is a part of milk. So what do we do is that we hydrolyze the milk with HCl and then neutralize it with sodium carbonate. So what happens? What are we essentially making? You remember the making of paneer at home? You add vinegar, which is an acid. So that is exactly what being done is that you neutralize it with HCl you add and then you neutralize that HCl with sodium carbonate. It is very rich in sodium because you've added a lot of sodium carbonate to it, and it's very poor in tryptophan, which gets destroyed by acid. So you may have to add additional tryptophan to improve the quality. Or you can use the commercially available peptone, which is more defined because you know that this is what it contains and this is what it is. Right. Few people have answered my question. 14 ml, 25 ml, 20 ml, 20 to 25 ml. I think everybody is giving me a different answer. We'll come more, let more people write and we'll come to a consensus at the end. So then we come to the meat extract. Now, what is a meat extract, what is yeast extract, and what is malt extract? You will find that these are given only in the older book of Mackey and McCartney because majority of the labs and the institutions now use ready-made media. So we don't actually require these, but you should know as a PG student as to where they come from. So meat extract is again a highly concentrated meat stock which is made usually from beef. It contains certain protein degradation products, inorganic salts, carbohydrates, growth factors, and it also contains certain gelatin, peptones, proteases, nitrogen compounds, accessory growth factors, and some carbs. Yeast extract is that you use baker's yeast and you wash these cells and then you extract the amount from there, and it basically contains amino acids and certain growth factors and salts. Malt extract, again consisting of maltose, what you see normally in children food additives for milk, something like Bonvita and Horlicks actually contain malt extract. It's in maltose, so it's majority of it is sugar. So remember when you give these additives to your children, remember how much sugar you're pumping in. So it has about 50% of sugar, it has starch, dextrin, and again some glucose and very little protein. 5% protein product only. Now, coming on to if my bacteria is very fastidious, we all are very, very, very fastidious. Ask your mom and she'll tell you, you don't eat methi, you don't eat this. So we are all very fastidious. Similarly, bacteria are also very, very fastidious. They may require some extra nutrition, like you eat your pizzas and burgers. They are not nutrition, but they do bring out that zinc in your food. Similarly, we have blood, serum, where this material is added to cover that extra nutrition for fastidious bacteria. So this material should be collected aseptically and rendered non-coagulable, traditionally by defibrillation. Defibrillation, how is it done? You shake the blood in a bottle containing sterile glass beads. The fibrin gets deposited on those glass beads and the um, blood gets coagulated. You can also add oxalate and citrate, but it's got its own problems. Bacteria may be utilizing citrate, and then the blood may clot later on. So but you have to use it to 60 milligrams for 10 ml of blood, which is used. Now remember, if you're using human blood, it may contain blood-borne viruses, antibiotics, antibodies, and a very high amount of glucose, especially if the blood has been collected after a meal or is from a diabetic patient, because you usually use discarded blood from the blood banks. You use human blood. Which other blood can you use? You can use sheep blood, which is the most commonly used blood. You can also use oxen and rabbit. Now, what is there any advantage of the other? Rabbit blood is usually used for extracting complement. Oxen blood is used in countries where oxen is a primary animal for food. uh, Rabbit blood is non-viable due to amount. How many rabbits are you going to bleed to get 50 ml of blood or 150 ml of blood? That's going to be a problem. So sheep is very adequately placed. Horse blood is used in EU because they have those stud farms from where they get this blood. In India, it's a problem because horses are not bred for recreation or anything. They're hardly used, so it's not usually preferred. So purpose is to give nutrition, and you can use any type of blood. In India, we prefer to use 5 to 10% sheep blood, and many companies now supply ready-made blood which has been rendered non-coagulant by defibrillation, and they supply them in packets, and you can use them. You can also serum, if you're using, you have to sterilize it by filtration after collection, because many a times it may just happen that the serum is not very sterile. So based on all these, how do you classify your media? First, of course, yes, on consistency. It may be liquid media, solid media, or semi-solid media. Based on growth requirements, they may be classified as routine media, or they may be defined or synthetic media. Defined is that they are simple synthetic and complex synthetic. Routine media is when they are prepared from meat extract or peptone, and they have a standard formula. So you will have a simple media, basal media, enrichment, and so on and so forth. This is something we've all grown up. Simple is that it contains only carbohydrate, protein, source, some electrolytes like nutrient agar. Enriched is when you've added blood and or serum to it, like a Loeffler serum slope or blood agar. Enrichment is liquid media, which doesn't contain any inhibitory substance, but by virtue of its properties, maybe by virtue of pH or by virtue of uh, the temperature, it tends to retard the growth to a certain extent. And then selective media, which has got an agent which is going to inhibit the commensal. For example, in Thair-Martin medium, there is something added to it. In SDA, which is a selective media for fungal, there are antibiotics added to inhibit bacteria. Differential is where you can differentiate. It is whether it is like pink colony or non-pink colony. Transport is, of course, for transport, and anaerobic is, of course, for anaerobic organisms. Then what are synthetic media? Synthetic is chemically defined media. Like you get in your Go to your media room and you will find those dabbas which are there, which contain powdered media. That is your synthetic media. It could be simple, where there is a box of simply McConkey or Newton agar, or it could be complex, that it has a lot of things, but it may and required addition of some other compounds like amino acids, and you often get media into two. So let's come to these one by one, and you know these examples very, very well. But what I am going to tell you, which is different from you, is what types of nutrient broth are there. Another, again, a question which is very commonly asked: what types of nutrient broth are there? One is meat infusion broth. What is a meat infusion broth? You allow the meat particles to boil and you take the aqueous extract of that lean meat where all fat has been removed, and you add peptone to it. That becomes meat infusion broth. So now you know what is a brain heart infusion broth. Means that the animal's brain and heart has been allowed to infuse for a longer time, and the aqueous extract of that meat is added to peptone. Meat extract broth is that you use commercially available peptone and you add commercially available extract, which is Lab Lemco. Combine the two, mix it in water. What is a digest broth? The same aqueous extract which you got from top, you add another proteolytic enzyme to it. So what will happen, that everything which is all proteins which are there in the meat will be digested by this enzyme. These are usually pancreatin, like it does in our body, and this will then become a digest broth. Now these terminologies are fading slowly as we are leaving traditional microbiology behind. Now, what are the various uses of basal media? You can use them for testing non-fastidiousness of bacteria, that yes, it doesn't require anything else. They can be used for preparation of bases for many media. For example, nutrient agar can be used as a base for blood agar. Sometimes you want to study the bacterial growth curve and you may study a nutrient broth. Nutrient agar is a preferred medium for performing biochemical tests like catalase, oxidase, or you want to do slide agglutination. You want to study the colony, how good the colony is. Does it produce any pigment? Does it produce a diffusible pigment or a non-diffusible pigment? Then, if you lower the amount of this thing, you can also use it for motility testing. Lower the amount of agar. Then you can also use it for stock culture, or you can first to study a microaerophilic organism, something which makes a semi-solid agar. That is also a basic. Now, enrich we all have deliberated quite often. Now, remember, when you add egg to any media, it becomes enriched. It also acts to absorb the toxin which are released, the toxic fatty acids. More than providing nutrition, it basically absorbs the toxins, and that is where the role of egg comes in. So you can have a serum peptone water, you can have blood broth, serum agar broth, glucose agar and broth, Todd Hewitt meat infusion broth for streptococci. So many examples. Now, if you look at blood agar, we understand that blood agar can also be a differential medium in addition to being a enriched medium, because it's approximately 5% that we normally use 5 to 10%. You can also go up to 50. Where exactly do you use 50 or 40% blood agar? Again, put your answer in the chat box and we'll take it up. It Why is it differential? Because it gives you whether it is alpha hemolytic colony or beta hemolytic colony. Now there are two ways of making a blood agar. One is a single layer agar. Single layer means that it will take a lot of time to dry and be ready in the lab, and it will require a lot of blood, because you will make 5% in say 100 ml of 95 ml of nutrient agar base and 5 ml of blood. You'll mix it, you'll pour it, and it will become a very thick layer. And you will not be able to appreciate the hemolysis so good, because it will block the light against which you are seeing hemolysis. Double layer is that you pour a layer of melted nutrient agar as 50%, say 7 ml, and followed by a 10% blood as a second layer if you're making a 10% blood agar. This requires less amount of blood, and it gives you, because it's got a background which is solid white, it gives you a better viewing of the hemolysis or even of the pigment. So even if you have a diffusible pigment, it gives you a good this thing. So then comes your enriched media में chocolate agar. What is chocolate agar or heated blood agar? It is something which is in nutrient agar molded to 70 degrees and you add blood to it and keep mixing till the temperature reaches about 70 and you pour it. You can put it in a water bath or something so that the whole blood, when you're mixing it, gets lysed. And what it does is that whatever is trapped inside the RBCs comes out. So that is the whole purpose of for highly fastidious organisms who can't even, I can't eat my food even with spoon. I need somebody to feed me. So there are certain bacteria who require that, like Haemophilus. Then there is a lysed blood agar. Lysed blood agar is also made similarly. How is it different from chocolate agar? Another PGY question. You heat blood agar at 55 to 56 degrees for an hour, or you alternatively freeze or thaw, or you add saponin to your blood agar mixture and and then add to nutrient agar to pour a lysed blood agar. Where is lysed blood agar used? I'm not seeing any answers. I did ask another question also. So, lysed blood agar is often used for antibiotic sensitivity for these fastidious organisms. Then you have egg-containing media, the Dorset egg media, egg saline media, Lanston Jensen media. So, whenever as a PG you are asked egg-containing media, do go beyond Lanston Jensen. You're not an undergrad. Then you can have Loeffler's serum slope, which contains serum, 75% glucose and nutrient broth. And it is, remember, LJ media and Loeffler's serum slope are not sterilized by insipissation. They are only solidified by insipissation. For sterilization, you filter out the serum and the rest of the elements you prepare by taking all sterile precautions. Insipissation is different from solid sterilization. Remember that. It's a nutrient poor media. Very often you are asked this question that if it is an enriched media, why is contains serum, but then why do granules grow in this, and um, why is it considered a nutrient pure media? Because basal media has got a very low sugar concentration and there is hardly anything here. So that is why it is considered very low. Plus, it's got glucose in it. So the moment bacteria starts growing, the glucose gets metabolized and you get acidity. And so it's hardly providing any nutrition. At the most, you can call it's a solidified version of enrichment medium, but it's not a very good enriched media. Another enriched media is Muller-Hinton agar. How does it get its without blood? How does it get? It was originally made for Neisseria and then it came out to be used for Kirby Boyer after adjusting the cations. That is why remember we always say cation adjusted Muller-Hinton agar or cation adjusted Muller-Hinton broth because it was the original media had all those cations which were required by Neisseria. So it primarily contains starch, it has beef infusion, it has casein and agar. So the nutrition is provided by casein, solidification by agar, and by beef infusion also provides nutrition. Starch absorbs again toxic fatty acids and also provides complex carbohydrates for bacteria to grow. All right, now coming to an enrichment broth and a very interesting graph that you see here. Now, this is a liquid media which may have certain inhibitory agent in the form that it's not inhibitory to the growth but could be inhibitory in terms of condition. For example, alkaline peptone water has got an alkaline pH. Now, let's take the example of alkaline peptone water and move ahead for Vibrio cholerae. Now, this is a situation where you have inoculated a tube of alkaline peptone water. This is a very poor version of bacterial growth curve, I agree, but it's just to explain to you. So, what happens after a lag period is that the bacteria starts multiplying. And when the bacteria starts multiplying, what actually happens is that the commensal bacteria are too many. This happens in a normal medium and not in an enriched medium. So, what happens is that this, which you see here, the red line, is commensal because the number of commensal was so high that they start shooting up. So when you subculture from any of this, say 4 hours to 12 hours, you will see a lot of commensal and you will not see any of the pathogen. This happens in a normal media. Now, what happens in a what do you say in a alkaline peptone water? Let's take the example of alkaline peptone water. Now, let me come up with a pen and show it to you. Now, if you have an alkaline peptone water, what initially happens is that there is a lag phase where all the commensal are running, and this is it's going ahead, it's going ahead, it's going ahead, it's going ahead, and later on it takes this form. All right. Now let's see what happens to our pathogen with the help of a black color. So what happens to a pathogen? Because the lag phase will remain the same. So what happens is that within say about 1 to 2 hours, the pathogen starts growing up because the commensal is getting inhibited either by the alkaline pH at which the commensal can't grow. Taking the example of APW. Now in APW, you want to isolate Vibrio cholerae, which is from E. coli, which is a commensal. So what you are doing here is that this pathogen is your Vibrio, which grows very well in your alkaline medium. So what's happening? The Vibrio is growing, growing, growing. Now at a certain stage, say about 8 to 12 hours, when you've crossed this and about 8 to 10 hours, the alkalinity has started going down. Why? Because the organism is utilizing the products, creating byproducts which are acidic in nature, and the pH has gone down. The more the pH goes down, the commensal starts shooting up. You see this commensal starts shooting up and they start growing. And whereas your Vibrio cholerae stops growing because your pH is not now conducive to your growth. So if you subculture at say 12 hour or 24 hour, what will happen at this stage? Suppose this is 24 hours, what will happen? This is not ready. This is commensal, which are more. But if you subculture at 4 hours here, near this arrow, if you call subculture, then your pathogen is more. So this is the principle on which it works. It delays the bacterial growth curve of your commensal, thereby allowing your pathogen to grow. It doesn't inhibit the commensal. So after 8 to 12 hours, the commensal has overgrown the pathogen. Now, where is selective media? Where is it used? How it is used? I'm going to skip this. You all have to ultimately will be able to mug up this, the Lowenstein, Jensen, and so on and so forth. Now, coming on to transport media. Transport media has to be completely non-nutritive because the moment the bacteria gets nutrition, they start multiplying, the pH changes, and it becomes inhibitory to the organism. Secondly, it should be easy to make and carry. So make it in a small tube or make it in a small test tube or a screw cap tube. It should be containing non-inhibitory substances. Bacteria will not multiply, they will only remain viable. And it is good enough for say 2 hours or 4 hours till it has reached. So Pike's medium contains sodium azide and crystal violet, which inhibits GNB. Emmy's medium or Stewart contain charcoal and they allow the growth of Neisseria. They maintain the growth of Neisseria, do not allow the growth of other commensal. In Venkatraman Ramakrishna medium, or the autoclave seawater, the salt is so high that it doesn't allow other organisms to anyway multiply. Shigella and Salmonella buffered glycerol, saline, and Caribbean medium. Some of these transport media can also act as an enrichment media. For example, alkaline peptone water can act as both. It can transport as well as. In that situation, they will allow some amount of multiplication of bacteria, but not a true transport media. Transport medium is like an Uber. You hired it, it dropped you there. That's it. It didn't do anything to you. If it did, it will become a national news next day. So, exactly like an Uber, it will take the sample, maintain the organism, and transport it to the lab. Now, if you look at what is Amy's and what is Stewart, some question which you will definitely be asked. Amines replaces the glycerol phosphate buffer, which is bound in an organic buffer. Amines has got charcoal, which neutralizes toxic material. As I said, it absorbs toxic fatty acids and improves recovery. Amy's performance is better, especially if there is a delay. It works beyond 2 hours also. Amy's lacks methylene blue, which is present in the Stewart formulation, and Amy's usually include calcium and magnesium, which control the bacterial formation. What is common? Both are semi-solid, both are non-nutritive, both are low nutrition media because we don't want them to grow. Both use a base of sodium thioglycolate to provide a reduced environment. Now, another transport media is Robertson cooked meat media for anaerobes, but that is for some other day. Now, differential is that either they use an indicator to differentiate between two types of bacteria, like McConkey for LF and NLF. CLED again uses certain advantages of blood agar and McConkey. It combines both the things, and it's an electrolyte deficit medium. Remember, that is why it inhibits swarming. Then anaerobic culture media, as I said, chopped meat particles and unsaturated fatty acids. Details we will do when we do anaerobic culture methods. So this is how it looks like: saccharolytic, proteolytic, that is. What are the other anaerobic culture media? Thioglycolate medium. You have to keep the redox potential low so that the reducing agents are added to this. Then there are anaerobic blood agar or PHI agar, neomycin, egg yolk, phenylethyl, and bacteroides. Now, how do I make sure that the quality of my media is good? You know what happens at home when mom or a maid cooks food? We all say this has got more salt, this has got less salt, this has got more oil, this she only puts oil in the food. Your parathas are so laden with butter and ghee. So what are we comparing it with? We are comparing it with the quality, with something. Sometimes we say, this person cooks better than my cook. This person has got a better, makes a better paratha or a better dosa as compared to my mother. So, how are we comparing this? We are comparing this because we want the quality of one with the other. So, when we need quality control, remember when very often students get confused that if we're getting a ready-made media, should we do quality control of that media? In the chat box, please, if you're getting a ready-made media, should you do a quality control? So the manufacturer has done a quality. Why should we bother? So many of you are saying yes, ma'am, but the manufacturer ne nahi kiya kya? Manufacturer did it. So why do we need to do it again? User has to assess the property. You know, whenever you buy a car, you go and drive the car, no? You see it suits me or not. So whether your media suits your requirement or not, you have to see it. So how do we do? This is again a very important PG question. Quality control of commercially prepared media. Now in quality, there is, if you look at the CLSI M22 guideline, which talks about the quality control of commercially prepared media, there is an exempt media category and a non-exempt media category. Non-exempt is commercial media which is documented by user, and the quality control performance may vary from lot to lot. You could take a picture of this slide or a screenshot if you're using your phone to log in. Non-exempt media requires complete user QC because you require confirmation of satisfactory performance with recommended organisms. Exempt is that it is exempted from the quality control. So you just give an advisory that you monitor for fastidious organism or specialized, but otherwise it is uh, a commercially prepared quality assured media. But that does not mean, the M22 does not say that you don't do any quality check. You can do if you want to do, or if your lab requirement occurs, then you can do. Now, what is exempt and what is not exempt? In general bacteriological media, you see blood agar, chocolate agar, thioglycolate, ureas. If you get these ready-made, they are exempt. In brain-art infusion broth, blood culture broth, biphasic culture, whatever you get from a certified this thing, you get. Now, there are two things to it. One is that we will have a media which has been supplied by the supplier. But here, the issue is you may get issues with your lab. That, okay, my brain infusion broth, which I bought from the supplier, is not supporting. So, in that situation, you may be required to do it. But the non exempt, you have to do QC before you go ahead. So it's one, it may be a regulatory expectation. That is why I said, you tell me why are we doing it, and we have certain answers. Oh, okay, we want to do double check. There is no point of doing double check, but there may be a lot to lot variation. Then maybe the manufacturer wanted us to keep that media at 10 degrees or 20 degrees or 15 degrees, whereas my lab is without AC and it's lying in 45 degrees of summer of Delhi. It's lying on the shelf, so it maybe it has deteriorated. Then quality of the raw materials which I'm using, say water, is contaminated. I'm after all making a dehydrated media in water only, na? So maybe it has deteriorated. It's got different applications in different environment. Many a times we realize we never asked for of this type of McConkey, but we got another one. So unless you do QC, you will not realize what's happening. So, if you have an incoming raw material, you've changed your base. If you have changed a lot, a batch has changed from the manufacturer. If you've done an additional treatment that your lab is a lot of growing contamination and you've irradiated it and you've done UV light to assess the delivery like heat shock or cold shock and to assess changes to storage conditions as part of the shelf life study. You want to know when does it expire. What are the quality control parameters initially? There are physical parameters that you look into. For physical parameters, for solid media, you just look, does it make excessive bubbles, or there are pits, or if there is an unequal filling of plates. When a new person goes into your media room and suppose your routine one is on leave and somebody who's not routinely going to media room pours plates, one plate will be 5 mm, the other will be 4 mm, the other will be 5 mm. So this irregularity may be there. The media may have overdried or dehydrated and it is cracked. So sometimes when you pick up a plate, you will find that it shows fine cracks on its surface. Sometimes you've measured 1000 ml because 60 gram had to go into 1000 ml. You added to it, but somewhere down the line it became 900 ml. So the gel will become more solidified, or the reverse might happen. Sometimes you put the plates in the fridge and go away for weekend, and you come back on Monday and you realize half of your plates are frozen. So all these you have to check immediately. Either they have been poured or they have been delivered. You should do this. Liquid media, you look at the clarity of broth. Hope there is no turbidity, there are no settlements if there should not be. Very little deposit should be there. And you can also check pH pre and post sterilization, because during sterilization the pH falls. And of course, you do sterility check and growth characteristics. So, how we do it? Visual inspection, as I said. Again, you can, for every 20 plate, you remove one plate and do a visual inspection. Is the petri dish intact? Is the agar attached to the bottom of the dish? That means that too little material has been, too little water is there. Blood containing medium is opaque. That means too thick. It's not 10%, it's maybe more than that. McConkey should be light pink in color. If it is dark pink, that means media is more and powder is more and water is less. Minimal moisture in the package, not frozen or desiccated. There is no visible contamination. Agar at least 3 to 4 mm should be there. The surface should be completely smooth and there should not be bubbles or cracks or precipitates. If your petri dish is damaged, cracked from the side, then it's going to attract contamination during incubation. The agar is very loose, that means there is too much of water. Hemolysis of blood has already occurred, that means too hot media has been poured in, blood has been poured in very hot condition. The color differs from characteristic appearance, probably a pH problem. It should be clad, should be light green in color, but it is dark green, so it's probably pH. It's all about the indicator and the pH. So maybe nothing has been utilized by the bacteria, but the pH has changed because something has gone wrong during preparation. If there is too much of moisture, it's going to attract contamination when you incubate it. And if there is a frozen plate and you don't know whether you get any nutrition or not, or there are uneven plates, from one side it is 4 mm, the other side it's 2 mm. If there are presence of any precipitates. So for every 20 plate, you remove one, do visual expansion, decide and record. If you think that maybe there are certain precipitates which are there, you may have to do it again or you have to make it again. The storage conditions are important because routine storage should be mentioned by the manufacturer. So you have to check your fridge whether it is maintaining the temperature. Storage conditions may affect drying out. There may be chemooxidation due to physical factors, or there may be a photooxidation from sunlight. Then there can be, how do you do sterility check? Sterility check is that you incubate at 35 degrees for less than 72 hours. You read and record the results. If there is any growth, you call it unsatisfactory. What do we do it? If there is a batch is less than 100, you do 5% of the lot. If it's the batch is say more than 100, 200, 300, 150, you take out 10 plates. And what do you use? You use the same microorganism panel which you have the ATCC or the control strains for normal routine media. For specialized, it is mentioned in the pharmacopoeias what you should do. So, what is the media used for? What type of organisms are expected? If you're cooking chocolate agar, you will have to use Haemophilus on that. Or if you're using or pneumo or meningo. But if you're using McConkey, maybe the ATCC E. coli will do. What all do you have interlaboratory consistency? You can have, you can use any of the standard cultures. The problem here is that they are very costly and difficult to maintain. But the advantages are that there is very minimum variability between the labs. The other thing you can do, you can also go ahead for interlaboratory comparison. You can, if you have say another lab close by or your sister lab, you can also do it comparatively. Then environmental isolates or wild types, there can be advantages like you can also use environmental isolates because if you're specially testing a new media than what is found in the environment, a completely pan sensitive strain you can stock and keep and that can be used. Disadvantages could be that it is costly to maintain, it's not true wild types and do not always grow. So how often to rotate this, that could be a problem. Now we all know how to maintain these microorganisms. This we've already 50 minutes into this. How to maintain these cultures is also another story. And this is the way how you do it. These are pictures from CLSIM 22. It's not freely available, so please remember that these are the methods that I use. That you inoculate each tube with 10 microliter of primary suspension, and you then do a subculture and you look, and there should be technically no growth within 48 hours of incubation. Then non-selective media, you prepare a 1 is to 100 dilution of the phosphate saline. Then non-selective media, you prepare a 1 is to 100 dilution of the phosphate saline, the in a sterile saline, and you inoculate the media, whatever this media you're using, and you look at the colony morphology and allow them to incubate for 24 to 48 hours of incubation. Now comes your issue. You sab to kar liya. Now, how do I troubleshoot? What has gone wrong with my media? If my media is contaminated, should I throw the complete lot? Because you remember, I checked only 5% or 10 plates. So, what do I do? One prudent technique is that we keep the media in the incubator for 24 hours. Whatever doesn't show any growth, you can use it if the batch is too large. But if you see that there is too much of contamination and more than 25% of media is contaminated, then you have to change the lot. You can't help it. And if you're getting it repeatedly, then you will have to probably contact the manufacturer. The rest of the things, like you check your autoclave, you check your controls, that is going to happen. All temperature, what is the indicator, what is the commonly used, what is measuring, all those questions you will have to answer. Now, certain media, you will say that we have quantitative media or AST, then up to 3 days and up to 5 days. All right, I'm going to skip this. This is already covered. All right, this we will skip. Sorry, I'm not going to cover this. So if you're challenged with a 10 CFU or 10 to 100 CFU, the other quality could be that your media fails to grow organisms. So here you will have to give a lower level challenge. Is it able to grow even 4 organisms of Haemophilus? So here you will have to be very careful. Then pass and fail criteria. When can I report the result? Inoculum is outside the range, incorrect incubation temperature, impure culture, microorganism does not grow. Should I reject? Should I repeat? These are the day-to-day procedures which you will have to follow. And so we'll not go ahead with this. And with this, I will end the. If you have any queries, please put it up in the chat box, or you can even unmute yourself. We are not too many. We did have a few answers. Yes, to double check, now you know what all situations. I recommend that you, if you can, try to get the CLSI QC. There are some material which is available, although the document is not available on the net. Any question, anybody, or can we end this? Culture methods and biochemicals we will cover in the next class. I did not cover it here because I felt it will become too long. Which method to follow to check pH? Yes, if you're checking pH of the media, always remember, never put if you're using a pH electrode or a pH paper, never put it in the whole lot. Take a small amount out and do it. And you should do it immediately after the media has started cooling down on your lab bench after the autoclave. If you do it previously, then the pH tends to change during autoclave. So always remember that if whether you use paper, whether you use electrode, take a small amount out in a petri dish or in a small tube and then check your pH after the autoclave, after it has cooled down to room temperature. Any other question? We will take another class for pH, culture methods, loops, materials. Any other question? All right. Thank you so much for joining in. Good to have you. All the best in microbiology. Which question, Dr. Payal, which question you want to discuss? %50 agar for Haemophilus, somebody has written. 50% agar is usually for Bordetella. 50% sheep blood agar is for Bordetella, not for Haemophilus. I think that's the question I asked, no other question. And the other one was how much media is needed for a 90 plate. I got very variable answers: 14, 25, 20, 25. I got very, very variable answers. Think about it. What should be the amount? 20 to 25 ml is the answer. All right. Thank you so much for joining in.